Okay, physics and integrals. So I'm going to make, I think it's going to be 2 videos on integrals, so to show you how to use them, in both the definite and indefinite, and then I want to get you comfortable with the idea of what a constant means. And then there's only a few of these that we'll do. So first semester, the complexity is not as serious. Second semester, we'll do some more, but you'll see it then by then in your math class. So an integral. So I like to think about this in terms of an example. So let's think about the example that we had where we're using the derivative. So if I have something that's, I don't know, say position versus time graph, and I have some function that represents that at any point along that function, I can get the slope, and I can end up with a velocity graph that represents that. So again, the slope for my position time graph tells me velocity, and this is derivative, right? So my slope is the derivative, so the rate of change is something. The only difference is when we talk about slope, we're talking about a long distance, and when we talk about derivatives, we're talking about really tiny, short things, so it's almost instantaneous. So the other thing that we've done with the graphs is that we can look at this area under the curve here, and that area under the curve will tell us the displacement, right? So my area under the curve is going to tell me my displacement. And this is what integrals are doing. So the integrals are a fancy way of calculating the area under a curve. And it's going to be doing the same thing. So this is going to be my integral. And a lot of times we'll call this an antiderivative because, well, it's the reverse of a derivative. So you should be able, if you take the derivative of something, you should be able to take the integral of that and get back to the same derivative. So one way to test integrals is to take the derivative and see if you get back to what you started with. So I will call this integrals, or antiderivatives, means the same thing. Derivatives. So this is what we're going to do. So let me describe for you how we do this. And there are going to be surely a couple of different styles of doing these. We'll call it definite and indefinite. So definite when we know exactly what's going on. And we'll use it for pretty much the same ways that we would have for right now. We'll use it exactly the same way that we would have used area under the curve. So going from a velocity graph, I can get the area under the curve, tell me displacement. And remember, from an acceleration graph, it'll get me back to the change in velocity. So let me walk you through a couple of examples. So first, say we have a function for position related to time. It's like 12t squared plus t. So I can figure out at 0 time, I plug in 0, and I'm at 0 position. At time point of 1 second, I'd be at 13 meters. So it tells me that position, which is changing with time at this regular rate. So let's figure out the velocity of this, right? So to find velocity, I would take the derivative of this with respect to time, or see the rate of change of this at any time point. And remember how we do the derivative. So the most common rule is the power rule. So I'm going to take a look at this, 12t squared. Remember, I take that exponent, multiply it by everything here, and then subtract 1 from the exponent. So I'm going to end up with 12 times 2t to the power of 1. And then I'll take this, multiply it by that, and raise the exponent, or subtract 1 from the exponent, so I get to the power of 0. So I'll end up with just the number 1. So now I have a formula, 24t plus 1, which represents the rate of change of position, right? So we'll call this, this is my velocity. So at any time point, I can find velocity. So again, refer you back to earlier videos too to take a look at. So the antiderivative, though, is just going to be doing the reverse of this. So the antiderivative is going to be a way for us to get from this back to what we started with, right? So this is going to be the integral, and it would take the integral of a function, so 24t plus 1, and we'll do it with respect to something, right? So in this case, with respect to time. When I take the derivative of this, right, I'm going to end up with, what do I end up with? Notice I'm going to do the reverse. So I'm going to do the reverse thought process here. So here, I took the exponent and multiplied it, and then subtracted 1. So now I'm going to add 1 to this exponent, and then divide this by that. So I'm going to add 1 to the exponent, so I'll get t squared. I'm going to divide all of this by 2 to get back to 12. I'll do the same thing here. I'm going to think of this as an exponent of 0. So I'm going to add 1 to the exponent. I've got t, and then divide by that new exponent, which is 1. So I'm going to end up with t. All right, so this is pretty close to what we're going to do. And that's, I mean, basically, that's the, if you can do that much, if you can use the power rule in reverse, then you're almost there, right? So that's the most common thing that we're going to be doing. So, but the challenge is to understand what this means, right? So this is now telling me, here I've gotten from position to velocity. Now I've got from velocity. I'm going to be careful about this. This doesn't tell me position. This tells me my change in position. So this is my displacement, right? So let me think about it this way, right? So if we had an equation that was position with a function of time, we'll call this, I don't know, 6t cubed plus 4, right? Now I'm going to take the derivative of this to get the velocity. Let's see what the velocity is going to be, right? So I'm going to take this, I'm going to take the derivative with respect to time. When I do that, right, I'm going to end up multiplying by 3, so I'll have 18, subtract 1 for the exponent, t squared. This one, I can think of this as t to the 0. When I multiply by that, it's all 0, so that goes away, right? So I'm left with t squared, which is my representation of my velocity at any point in time, right? So that's good, but going backwards, we have a problem, right? So I want to be able to get from this back to this whole equation, but I don't have enough information to be able to do that. So here's the problem. So I'm going to take the integral of 18t squared with respect to time. And what am I going to get? Well, I'm going to get this. I'm going to add 1 to the exponent. So I got 3 t cubed. I'm going to divide by my new exponent, which gets me to 6. And that's all I got. Right? So did I get back to where I started from? Well, no, I'm missing the 4. Right? So remember, what this is telling me, this is telling me my change in displacement. And to get that extra value, I need to know some more information. So the way we account for this is we'll say, well, we don't know. So if I wanted to find the absolute displacement correctly, I would say t cubed. There's some constant I'm missing. I mean, I don't know what it is. I need some more information to figure that out. So there's some constant that I'm missing. So when we're going backwards for this indefinite integral, that there's some information that we don't know, and I need some piece of information to find. So if I told you that position x at 0, at time point 0, x is 4 meters, well, then you can say, great. So now I can say, well, this is my position function with respect to time is 6t cubed plus some constant. So I know x of 0 is 4, so I know 4 must equal 6 times 0 cubed plus my constant, and I can figure out my constant amount. Constant must be 4, and I can get back to the original equation. Okay. So that's one thing to be careful of. So one, taking integrals, and when they're indefinite, so I'll get to definite integrals in the next one. When they're indefinite, so we have to worry about the position. So think about this for a minute. So if I was to take the let's see. So if I have a velocity, say we just use this one, right? So 18t squared. So if I know my velocity at a specific time is 18t squared, and I take the derivative of that, what does that tell me? Pause it for a second. Think about it. Okay, welcome back. So so take the derivative. The rate of change of velocity is going to be acceleration, right? So dt of velocity. If I take the derivative of this, I'm going to end up with 36t to the 1. And I can think about the antiderivative should get me back to where I started from. So 36t. So if I take the integral of 36t with respect to t, all right, that now I'm going to do the reverse that I did for the derivative. So I'm going to raise 1 to the exponent. So now I have t squared. And I'm going to divide by that new exponent. So I'll get back to 18. And I want to add some constant in there because I don't know. So remember, this tells me something, and this tells me something. So what does this constant tell me at this point? Pause the video. Answer it. Welcome back. Right, so this tells me my change in velocity, and this one is going to tell me my initial velocity. So the constants, they mean something, they're important, and sometimes we disregard them. If I'm only interested in change of velocity or change in displacement, then the constant doesn't matter. But I need some more information to get it, unless I have a definite integral, and that's in the next video. See you then. Bye.